Hello everyone. Before proceeding to the further topics in the electrostatic chapter, let us just go back and recall the few concepts by solving a question. So consider a semi-infinite rod with positive charge and semi-infinite rod of negative charge having the linear charge density as plus lambda here and here minus lambda, and there is a ring So now given that the radius of the ring is r, mass is m. So what we are required to do is we are required to find out the charge on the ring so that the whole system is in equilibrium. How do we do that? See, we know that due to the semi-infinite rod, the electric field at R is K lambda by R due to this positive charge, the one angle is 0 and one angle is 90 degree, and this direction is downwards, and this direction is in this way. Sorry, this is 1 plus 0 and this is 1 minus 0. Yeah. So, due to this positive charge, the electric field is now. Similarly, if you try to find out the electric field due to the negative charge, this thing, we will find out that due to the negative charge thing, the electric field is in this way. So if you try to find out the net field, this and this gets cancelled. So ultimately it results in twice of this, which is equal to 2k lambda by r acting downwards. So suppose the charge over the whole ring is q. Since the electric field at every point is same, so we can directly sum it over up to all the charges. So the net force acting due to the electrostatic field is equal to q times 2k lambda by r, and its direction is downwards. Since for this ring to be in equilibrium, the net force acting on this ring should be 0. So what is the net force? Q times 2k lambda by r plus mg is the net downward force, and there is none other force present, so this should be equal to 0, which implies that Q is equals to minus mg r by k lambda. So if we put this amount of a charge over this ring, then this ring would not fall down, instead stay in that place. So now we found out the application. Like we have used what all did we use here? We used this formula that the E perpendicular is equals to k lambda by r times sine alpha plus sine beta, and E parallel is equals to K lambda by R cos alpha minus cos beta. Just to have a note, these formulas become very important while we solve the questions, and yeah, then it's very simple equating it, the net force to be 0, and then hence we get the answer. Now let us see the application of one more formula which we have studied earlier. Let me give you the formula first and then its application. So the formula is, see, we have told that for an arc of radius r and angle 2 alpha, the electric field is equal to K lambda by R sin alpha by 2. Okay, so what will the electric field, and the direction of the electric field will be along this line. Now if the charge is positive, it will be in this direction. Say if the charge is negative, it will be in this direction. So based on this, what did we tell? That for a semicircular ring, yeah. So the electric field here would be equal to K lambda by R times sine of pi by 2. So this is an important formula which you are going to use now. Based on this formula, let us try to solve a question. See, in this question, we are given that the configuration of the charge places in this way, where this is negative charge minus lambda, and it is positive charge plus lambda. So we are asked to find out the electric field at this point, center of the semicircular charges. So how do we proceed? See, we have learnt how to find the electric field at the center of a semicircle. Now we will try to use the same concept and solve this question. So what was the formula for the electric field? Electric field is equals to K lambda by R away from the body if charge is positive, towards the body if charge is negative. So see, now sorry, pardon, the question here says that this is this positive charge, sorry, yeah, and this is also positive. Whole thing is in lambda. Now see, let us divide this question, try to break this question in parts. First part, okay, so using that formula, what do we get to know? We get to know that here the electric field, the magnitude of electric field is equals to k lambda by r, and the direction is, see, since it is a semicircle we have, and the charge is positive, the direction is away from the body, that is downwards. So let us note here, due to first part, this is first part, this is second, this is third, and this is fourth. Due to the first part, the electric field is downwards and it is k lambda by r. Now let us consider the second part. Second part, what is the second part? See, we have a line here of length. See, now since this is 2r, so this would mean that even this distance is 2r and this distance is r, because the radius of the small semicircle is r and the radius of the bigger semicircle is 2r. So this distance would end up being r, and similar is the case here. So we have a rod, it's similar to a rod of length r having charge lambda, charge density as lambda, and we are asked to find the electric field at a point which is at a distance of r from the charge. Now if you recall, we have derived the formula for this case. At a D position, this length being L. So what was the formula? See, the formula was KQ by just check if the formula is correct or not. This was the formula for this thing. So here if we try to convert, see what will the Q become? In this case, Q is equals to lambda times R, and D is equals to R, L is equals to R. So here the electric field would turn out to be, see, K times Q is lambda R by D is R times R plus R. So this R and this R gets cancelled. It turns out to be K lambda by 2R. Direction is, since it is positive, it is in this direction. So due to the second part, it is in this direction, K lambda by 2R. Now let us find out due to the third part. The third part was a semicircle. Pardon me, I'm not that good at drawing. Okay, so of radius 2r. Now according to this formula, the electric field is equal to k lambda by, see, here r was the radius of that semicircle, but in this case now we have a semicircle of radius 2r, so here it will become 2r and the direction is upwards. So due to the third part, okay, And now finally due to the fourth part. See, fourth part is similar to that of the second part and it's almost the same. The only thing being the direction change. Now we require the electric field in this direction. Now since everything is the same, the magnitude will still remain the same and magnitude is equal to k lambda by 2r. Only the direction changing and it now to be this way. So the fourth part is now we have found out all the electric fields. Now we know that the net electric field is equals to the superposition of all the electric fields. Which is equal to, see, k lambda by r in downward direction plus k lambda by 2r in right direction plus k lambda by 2r in upward direction plus k lambda by 2r in left direction. So here see, k lambda by 2r in right direction and k lambda by 2r in left direction gets cancelled, and here it becomes net is equals to k lambda by r minus k lambda by 2r in downward direction, which is equals to k lambda by 2r in downward direction. So finally what do we say? We say that the electric field at this point is equals to k lambda by 2r in downward direction. So this way we find out the electric field of a given arrangement of system. So what do we take? The takeaway from this question is, given a combination of charge distributions, what do we have to do is find out the electric field due to every part and then superimpose them to get the final result. Now let's go on to use our earlier concepts to derive few results. We are going to find out now the electric field at the axis of a ring. Note that earlier we've told that the electric field at the center of the ring is equal to 0. So now what do I mean with this part? See, let this be a ring of radius r. Now at a distance x on the axis of the ring, I want to find out the electric field. Let the charge be q. So see, what we do here is we randomly take some element, okay? Let this element has a charge dq and it is such that, see, okay, yeah, so let this be the small element dq. Now what is the electric field due to this charge at the point, say O? We say that the electric field, the magnitude of electric field is equals to k times the charge is dq by distance square. Now distance square is r square plus x square, right? Now we have found out the distance also. Now the direction will be in this way, right? So if this is theta, this angle would be theta. Now let me consider a diametrically opposite point. Okay. Now due to this, the electric field will be in this direction, which would again make an angle theta. Because see, these are diametrically opposite points, so they would end up making like if we try to resolve, and the electric field due to any small element dq is the same. Since it depends only on dq and we are taking dq to be same thing, and r and s are constant basically. So for the diametrically opposite point, the net electric field turns out to be, it becomes E cos theta along the axis and E sin theta here, then E cos theta along the axis and E sin theta here. So for two diametrically opposite points, this component and this component gets cancelled, and net we get 2E cos theta along the axis, which is nothing but 2 times k dq by r square plus x square times, cos theta is equal to x by okay. Now see, if we take any point, it is very true that we can always find a diametrically opposite point to that in the ring. So we say that now which would mean that if we like this part takes the effect of this thing and this thing. So if I start here, taking this point would mean that I am taking the effect of this point also. Taking this point would mean I am taking the effect of this also. Taking this would mean I am taking the effect of this also. In that way, if I consider, if I start from here and go till here, would mean that I am considering the effects of this part also. Hope you are understanding. See, when I write 2E cos theta, 2E cos theta is not due to only one point, it's because of two diametrically opposite points. So for that reason, I while integrating the electric field, I consider the charge present only in the one half of the ring. So if I consider that, the electric field would be, it will always be the small electric field due to two point elements will be equal to 2 times kx dq by r square plus x square power 3 by 2. Now if I try to integrate it, the net electric field at the point x will be equal to kx by 2kx by r square plus x square power 3 by 2 times q by 2. See, understand why this q by 2 comes. This q by 2 comes because I am not integrating it to the whole part. I am integrating it only from here to here. Why? Because whenever I am considering a part, I also take the effect of the diametrically opposite point, and that is the reason I get 2e cos theta. Thus, here I take q by 2 instead of q. So this and this gets cancelled, and I get electric field is equals to kqx by r square plus x square power 3 by 2. And the direction is along the axis. This is an important result. Okay. Now there is a question based on this result which says that find the position of, find the value of x for which this electric field becomes maximum. At which point does the electric field due to a ring become maximum? So it's basically a mathematics question. Only thing that we should know that the electric field, or what is electric field at a point x. Before going to solve that question, let us analyze whether the expression we got is correct or not. What we got was electric field is equals to kqx by r square plus x square whole power 3 by 2. See, now if x equal to 0, it means that we are analyzing at the center of the ring. And we know that the E center was 0. Now do we get 0 if we put x equal to 0 here? Yes. So our analysis, our formula is valid. Now let us try to find out the maximum electric field. See, electric field is equals to k qx by r square plus x square power 3 by 2. Now for maxima or minima, what do? We first we take the first differential, like d by dx to be 0 and d square e by dx square. For since we are finding a maxima, this should be less than 0, right? Now what is d by dx? First take, it will be kq by r square plus x square power 3 by 2 plus kqx See, it is due to the chain rule. First I consider, I differentiate only x and write everything as the same. Then I do not differentiate x but differentiate the denominator part, which is r square plus x square power 3 by 2. And thus I get this. Now in this whole thing, if I take kq by square plus x square power 5 by 2 as common, I get here r square plus x square minus, this 2 and this 2 gets cancelled, minus 3 x square, which is equal to kq r square minus 2x square by r square plus x square power 5 by 2. Now, for the first differential to be 0 would mean that r square is equal to 2x square, which means x is equal to plus or minus r by root 2. Now, let us check the second differential, that is d square e by dx square. Now, see, let us write this somewhere here. We said that dE by dx is equals to kq times r square minus 2x square by r square plus x square power 5 by 2. Now d square e by dx square would be equal to d by dx of by quotient rule, it will become See, this would become r square plus x square whole power 3 by 2 if I take common. I get right. So this is equal to minus 4r square x minus 4x cube minus minus 4x cube minus r square 5 by 2 r square on substituting this value we find out that this is less than 0. Thus we say that at x equal to plus or minus r by root 2, the electric field attains its maximum value. Now if we try to plot the graph of electric field with x, so at center it is 0, it would come this way. It is a symmetric graph. This is minus r by root 2. This is r by root 2. Okay. Yeah. Now, next we try to find out the electric field due to a disk. Consider the disk having okay, and now we are asked to find out the electric field at the axis. So for this what do we do? See, we go to a distance small r, consider a ring of thickness dr, and we know that the electric field d, let the charge be dq at this ring. The electric field due to this ring is equal to k dq x by x square plus small r square whole power 3 by 2, right? And given that this is capital R. Now we are also told that the charge is uniformly distributed, which means that if the total charge is q, then q by pi r square is a constant, and which is equal to sigma. Now the charge dq at this ring will be equal to sigma times the area of the ring, which is equal to c. 2 pi r is the perimeter and the thickness is dr. So dq is equal to this much. Now what is sigma? Sigma is q by pi r square times 2 pi r dr is equal to dq. Pi gets cancelled. From here we substitute here and we get d is equals to kx. In place of dq we write q by r square times 2r dr. Okay. Now to find out, see this electric field is in the direction of the axis. Now to find out the net electric field, what we do is we integrate this part and this part, and here the limits of integration are 0 to capital R. So left hand side we get E, and right hand side, see I do the substitution, x square plus r square is equals to t square, which would mean 2r dr is equals to 2t dt, and x square plus r square power 3 by 2 is equals to t cube. Now the integration becomes, see, when r is equal to 0, t is equals to x. When r is equal to r, t is equals to under root of x square plus r square, right? So this becomes kx cube by r square times 2t dt by t cube. So this t and this t square. Now this is equal to 2kx cube by r square times, so integral of t power minus 2 is minus 1 by t, limits being x, root over x square plus r square. So after substitution the limit, we get the electric field is equal to 2kx cube by r square times plus 1 by x minus 1 by under root of x square plus r square. This is equals to 2k cube by r square times 1 minus now this is one type of denoting the expression. The other way is, see, what is k? K is equals to 1 by 4 pi epsilon naught, right? So this 2 becomes this 2, and we know that q by pi r square is equal to sigma. So what does the electric field become? See, this is sigma. Now consider the case where the dimension of this disk becomes very large, which means that r tending to infinity. So if r tends to infinity, then this term here would tend to 0 and electric field would become constant and is equal to 2 by epsilon, sigma 2 by epsilon naught, which is the case of a infinite plane. So the electric field at a small distance due to an infinite plane is equal to sigma by 2 epsilon naught, and the electric field due to the disk of radius capital R at a point x on its axis is equal to this in the direction along the axis. Okay. Now this is how we derived all these equations. Now I'll give you one more formula which is not to be derived, but it's good if we remember it. The electric field at the center of charged hollow hemisphere. So if the hemisphere is completely charged, with the surface charge density to be sigma, then the net electric field at the center would be down, like away from the body, perpendicular to it, and its value will be sigma by 4 epsilon naught. Now, if anyone of you wants to derive it, I will give you the hints to derive. See, to derive, consider go to a distance r from the center of take the angle theta and then consider a d theta strip, then try to find out the electric field and then integrate it, so you get this answer. But no need of derivation. If you remember this result, it's quite enough. Now let us move on to a new concept called as the electric lines of force. So, what are electric lines of forces? Electric lines of forces are imaginary or hypothetical lines which give the information about the strength and propagation of the electric field. So, they are hypothetical lines which gives us information regarding the strength See, here important, very important words are that they are imaginary or hypothetical lines. They won't occur actually in the environment, but just they are imaginary. And they give information regarding the strength and propagation of the electric field. But how do they give this? So, the electric lines of forces have a few characteristics of their own, which help us find out the information which we are talking about. So what are its characteristics? See, first and foremost thing which the electric lines of forces tell us about the electric field is, see, given that, say if someone says that the electric lines of forces are in this way, what would it mean? It means that if you consider this point, the electric field at this point is the tangent in the direction tangent to this curve. The electric field at this point is in a direction this way. The electric field here is in this direction. The electric field here is in this direction. So, what do they say? The tangent drawn at a point on the electric lines of force give us the direction of electric field at that point. Okay, and then see, now we have drawn this sound curve and told that the direction is so and so, but actually how are these electric lines is drawn? So these lines basically emerge from positive charge and converge at the negative charge. So, for example, an electric line of force like would be, consider if there is a charge plus q here and minus q here. This might be an electric line of force. And now in this case, see, if I try to draw a tangent at this point, I get the tangent in this direction. So I do not know which should be the direction of my electric field. Right? In that case, we can use this information that the electric field will be in this direction. Right? Yeah. So next point is the electric lines of force. They never intersect. But why do not they intersect? See, consider like if these are two electric lines of forces and they are intersecting. So what would that mean? It would mean that the electric field at this point is in this direction. Similarly, the electric field at this point is in this direction. But which is not possible. The electric field at a point will have only one direction. It should be either that or this. So, if at all the electric fields of line intersect, would mean that the direction of electric field at a particular point is given in two ways, which is not at all possible. And that's the reason why we say that the electric fields of force, electric lines of force do not intersect. Now, when we draw the lines, we say that the density of lines determine the strength. So now what does this statement mean? It means that, see, if there is given electric lines of force in this three ways. And this is a point A, this is a point B, this is a point C. So, see, we see that almost in a equal region, the number of lines are differing. Now, what does that mean is, see, since the density is higher here, so electric field at the point C is greater than, the electric field at point B is greater than electric field at the point A. So, this is meant by this statement. Now, this also depends on the charge. See, a few examples I would like to give here. See, if there is a plus Q charge, suppose the electric field of line are going in this direction, this way. Similarly, if it is a plus 2Q, so it will go this. The number of lines increases. If it is minus 4Q, see here the direction is going out. Minus 4Q, it's coming in. So we can see that, the number of lines concentrated near this charge is more than this and this. So basically, it also depends on the magnitude of the charge. It does not depend on the sign. Sign would only tell whether the fields are going out or coming inside, but the strength would depend on the magnitude of the charge. Now the last characteristics of the electric lines of forces is that they are perpendicular to the surface of the conductor. When? Not always. Suppose this is a conductor. If I consider electric field of line passing from here, so it would be perpendicular just near to it. After that it may be anything, like it may go this way, or maybe it perpendicular here and then it may go this way, it may go this way, it may go this way. So let it be anything, but near the very close to the conductor, charged conductor, the electric field of line will be perpendicular in direction. Now based on this information, like based on these electric lines of forces, we enter into a new concept called the electric flux. So electric flux denoted by phi is a scalar quantity. So it has something to do with the number of electric field lines. So which in turn means strength. So what do we say is, consider a surface of same area. Let this area be A and this also be A. So if the electric lines if this is the electric lines passing through this surface and this is the electric lines passing through this surface, let the flux here be phi 1 and the flux here be phi 2. We say that phi 1 is greater than phi 2. So phi 1 is greater than phi 2 would mean that the flux passing through the surface A is more than flux passing through the surface B. But it does not mean that, say phi 1 is 11 and suppose phi 1 is 11 and phi 2 is 8. It does not mean that the number of lines passing through the surface is 11. No, it does not mean that. It only means that the flux passing through the surface is more than this and it is proportional. The number of field lines passing through this by number of field lines passing through this may be 11 by 8. It is proportional, but we cannot find out the number. Okay, so this is the way we find out. Now how do we find out this quantity called flux? So mathematically we tell that the flux phi is equals to E dot dA. Now you might have a confusion that, see, we know that electric field is a vector, but what about the area? Like, see, what is A? What is this? A is basically the area, but how is that a vector? So see, consider the sphere, okay, and suppose if we take the small element, if we expand it here, we would get it in this way. Now this is a plane surface which has a normal which has a normal to its surface. So we define the area vector such that the area vector is equals to the area. See, for this, whatever is the area, let it be a area dot the normal vector, normal n cap. So area vector is defined in this way. Now we may have another doubt. See, the normal vector here can also be here. So in this scenario, what do we take? Suppose that the body is a closed surface, then the area vector is taken such that the vector comes out of the surface. So suppose if this is a sphere, the area vector of this element would be in this direction. Okay, so the flux is calculated using this formula. Phi is equals to E dot A. Which would mean that if this is the area and this is the electric field, so see, this is the electric field, this is the area vector. Suppose theta is the angle between them, so phi is equals to EA cos theta, right? Now consider scenario. See, when will the angle be acute? The angle will be acute if the flux lines are going out, which implies the angle is acute, so phi will be positive. The flux will be greater than 0. If field lines, not flux lines. If field lines are, then the angle will be greater than 90 degrees, so cos theta will become negative and the flux will be less than 0. If field lines are grazing, that is angle is equal to 90 degree, then we say that phi is equal to 0. Okay. Yeah. So this is the scenario. Now for a note, see, for example question, find out the flux, basic magnitude, we want the magnitude here, through an area of 100 square units in the XY plane if the electric field is equals to 8 I cap plus 3 J cap minus 4 K cap. Okay, so in this question what do we have to do is, see, we know that the XY plane, okay, this is X, this is Y, this is Z. Consider XY plane. We know that the normal acting upwards is in the direction of K cap. So the area vector here is equals to 100 times K cap, and the flux will be equal to E dot A vector, which is equals to 8 I cap plus 3 J cap minus 4 K cap dot 100 K cap, which is equals to minus 400. But since we are asked the magnitude, so the magnitude of flux is equals to 400 unit. And yeah, 400 units. Then now let me tell you a very nice way to solve a few questions. Suppose we are given that the electric field is uniform. Say it is this way. Okay, and we are asked to find out the flux through this surface. This angle being theta. So what we can do here is, okay, let me draw it a bit more in a way so that it's more understandable. Okay, so in this case, let the E be constant. So what will be the flux? Flux will be equal to E A cos theta, right? Now, what is A cos theta? A cos theta is the projection of this. If I consider this to be this way, like being this way, exactly plane. So this is its projection, right? Which is this angle is theta, and it is its projection. So whenever the electric field of line is constant, then to find the flux, we can simply do what is electric field into the projection of that particular thing for which we are trying to find out the electric field. Let me illustrate this with an example. So, see, consider a cone. Of height h and radius 2r, diameter 2r. Given that the electric field is constant in this direction and is E. Now find out the flux leaving the cone. So here again, see, the electric field is constant. So what do is we take a projection of this thing and then try to find out the area of that projection and then multiply the area of projection into the electric field. Now how do you find out the projection? For finding out the projection, see, imagine that what will happen if you flash a light from here. If you flash a light from here, on this screen we would get an image of a triangle. And what will be the triangle dimensions? The base would be 2r and the height would be h, right? So what is the area of this triangle? Area of this triangle is equal to half into 2r into h, which is equal to rh. So the electric field leaving this surface would be equal to electric field times the area of projection. Okay, now if in the same question, what if I say that let this all be the same? Okay. Now I say that the electric field is in this direction. Okay. Now what is the flux through the surface? So now again, what do? We flash light. So what do we get to know is, see, we will get the projection in this way. Dimensions. So what would be the area of this? This would be a circle and area would be pi r square. So the flux through the surface is flux is equals to E times pi r square. So these are a few techniques which we can use to find out the flux. Now this is all for today. In the next session we will learn a bit more about we'll solve a few questions on flux and then we'll go to the concept of potential. That's all from my side. Thank you.